Sample problem. Here we have a bridge circuit as shown on the figure. Find the current in each resistor and the equivalent resistance. All the currents here are initially unknown, but they are related by some function. So we first write the relationship of the currents with each other by using the Kirchhoff junction rule. We write the equations for each junction as equations A, B, C, and D. We can reduce the two currents and express them as functions of the other currents. From equation A we see that the current 4 is just equation A. From equation B we see that the current 5 is just equation F. Basically we have three unknown values and therefore we need at least three equations to solve this problem. Now we apply the KLR and we select some loops, and the choice of the direction totally depends on you. At loop 1 we have equation G. At loop 2 we have equation H. At loop 3, which is the largest loop, we have equation I. As you can see, we only selected a few loops despite that we can have more loops. The strategy here is typically done in a way that we reduce the number of devices necessary but must contain some or all the unknown. It is like choosing to have shorter equations since each term in the equation corresponds to a device in the circuit such as battery, resistors, bulbs, and others. A good strategy in drawing loops is to have a common intersection of the loops, like for this case they all intersect at the junction point C. We begin by simplifying the equations. Let us look at equation H, which will give us a simpler relationship of the currents 1, 2, and 3. We have equation J, which contains all the unknown. The other two equations contain only two of the unknown. We can substitute equation J to equation G and get equation K. Now we can equate equation K and I since both have the same currents, and we get equation I. We now substitute equation L to equation I and we have the current at resistor 3, which is -1 ampere. The negative value of the current 3 tells us that the assumed direction is incorrect and must be oriented towards the other side. We now substitute the obtained current I3 to equation I and we get I2. Similarly, we substitute the obtained current I2 and I3 to equation J and we get I1. We also do the same for equations E and F and we get the currents I4 and I5. Now we determine the equivalent resistance of the circuit. Here we apply Ohm's law, which is given here. But first we obtain the equivalent current is obtained using equation C, which gives us an equivalent current of 11 amperes. The equivalent voltage is just the voltage difference at points C and D, which is equal to the EMF, which is 13 volts. Now we substitute this to Ohm's law, we get the equivalent resistance of the circuit is about 1.2 ohms. Here we correct the direction of current at the third resistor positioned in the middle of the bridge circuit. Here we have a simulation of the problem using FET. We see that simulation also shows that the direction of the middle resistor goes in that direction. Simulations could help you to check if your solutions are correct or predict them. You can explore and examine the current of the resistors in FET sims.